Good morning. So this week we'll finish the chapter about motors, and the remaining few lectures we'll talk about system design, because I found out from experience that even if you understand the sensor, the interconnect, the actuator, you need still some people don't know how to approach a bigger problem if you have to design a system. So we have enough time. Actually, we did well on time, so we'll start covering system design from Thursday on. And after that, the week after, I'll give you the last assignment, and the last assignment is simply a trial exam, just so you'll be familiar with the format of the final exam, and this is 10% of the grade. Now, two people already approached me that it's very inconvenient for them to come to the date of the final exam. The 23rd is very inconvenient. So I set up for people who have a good reason why they can't make the 23rd. I set up an alternate date, the 16th, at 10 a.m. Okay, so if somebody really can't make the date of the 23rd, he'll get an equivalent exam. Not the same exam, of course, but an equivalent exam on the 16th. So come and talk to me after the lecture. Okay, so let's get back to motors. So what I want to talk a little bit today about is the characteristics of the different motors, because when we talked about DC motors, things were very simple. Just as a reminder, with DC motors, if we drew omega versus torque, things were very simple. They were either PMDC type motors, where the speed dropped a little bit when the torque went up. And the reason the speed dropped, I'm reminding you, because the IR dropped. Okay, so the more torque, more current, more IR drops. So the actual voltage the armature saw was dropping, so the matching speed to given EMF to match that also dropped. And as you recall, there was a family of curves, and this is V1, V2, V3. As you lower the voltage, the curves drop, and this was PMDC. And if we went to series wound, there was a family of curves like this, and again this was V1, V2. Okay, so this was very simple, because the input, the only parameter was voltage. He gave the motor a voltage, it took as much current as it needed based on the torque. Okay? Now when we talk about rotating field motors, things are a little bit more complicated, because if we say, let's start with a synchronous motor. If we draw omega versus torque for a rotating field motor, so since it's a rotating field where the magnet of the armature is locked to the rotating field vector, when you change the torque, the speed doesn't change. Okay? Now, I said that at this point, I mean, simplistically, you tend to draw it like this, that at a certain torque it breaks lock. It can't follow anymore, because remember, the rotating field creates the equivalent of a rotating magnet. The armature is another magnet, and the one magnet follows the other. But at some point, there is so much torque, the magnet can't follow, because the torque is more than the torque the two magnets can generate. Remember the analogy. The analogy was, you have a rotating magnet NS, and the rotating field looks like a ring with another two magnets on it, and this ring rotates and this is following, but it starts winding up. As it follows, it starts winding up. So let's say if you have a bigger torque, the poles are like this, NS, and this is a magnetic attraction, but at some point, if you put more and more torque, it just breaks lock, and once it breaks lock, it loses all torque. Okay? And this is, does somebody remember what this angle is called? It's only a week ago. Power angle, yeah. Okay? Sometimes it's called torque angle in some textbooks, but it's usually referred to as power angle. So this power angle can only go up to 90 degrees and then becomes unstable. Now the reason is that it's clear to everybody that if the power angle went to 180 degrees, the torque will be 0, because 180 degrees, instead of attracting, it will repel. If this S ends up here, instead of keeping attracting, it will actually repel. So clearly, if the power angle, it starts winding up, and it goes all the way to here, it wouldn't attract this it wouldn't attract this pole anymore. It will actually repel it. So the power angle at 180 degrees has to be 0, and at 0 is also 0. Now the reason power angle so again, this is, I'm drawing something else now. I'm drawing torque. It's not the same graph. I'm drawing torque versus theta. So at 180 degrees 0. At 0 is also 0, because when the two poles are aligned, a little bit of movement create very little torque. It's only when the magnets start separating there is enough torque created. Okay? Because if the poles are aligned, a little bit of movement doesn't change the flux. You don't change the flux, you don't generate the force. So it's 0 here, 0 here, and it turns out it's symmetric. But you can only use this part, because here it collapses, it can snap over. So you can really only use power angle from 0 to 90 degrees. And as you increase the torque, it starts winding up until it breaks lock. And when it breaks lock, it starts vibrating. It loses torque, just like a stepper motor when you stall it or when you try to run it too fast. So what really happens, it doesn't go down. The line doesn't really look like this, because if there was really a solid line here, it would imply that you can use a motor as a constant torque motor. See, this line implies that torque is constant and you can change the omega, or omega changes. Okay, there are such motors which are used as constant torque, but that's not really what happens. What happens, it collapses. If you reach this point, so this power angle here, theta is 0, because there's no torque. Let's say here theta is, say, 45, and let's say here is theta is 90. I mentioned to you before that's actually a half sine. Okay, so theta is 40. Okay, so at 45 degrees you have 0.7 of the torque. So it'd be more accurate to draw theta 45 as this point, because sine 45. Okay, but at this point it doesn't go constant torque, it actually collapses. It wants to go back to 0 torque and 0 speed. So there is really no graph here, because everything collapses. Right? You can't use this part of the graph, it collapses. So it really looks like this, and then who knows what happens. It either collapses this way or collapses this way, but that's not a stable part of the graph, it stalls. Now, okay, now if you change the voltage, okay, not the speed. Omega is a fixed. Let's keep omega constant right now. It's a rotating field, a constant speed, but you lower the voltage. What will the graph look like? I want to generate an equivalent graph here where I operate the motor on 3 voltages. So if I have an induction motor which is designed to work on 208 volt, like industrial voltage, and I give it 100 volt, what will the graph look like? Yes, please? Exactly, because the speed cannot change. It's a synchronous motor. All what happens, it collapses here. So instead of collapsing here, it collapses here. So this will be V1, this will be V2, because it can't generate any more torque, because there's less current, less torque. So the power angle winds up faster and it collapses. Okay? So the family, it doesn't really have a family of curves. It just reaches a different torque and collapses. Okay? Now, what happens if I want to change the speed? What do I have to change? Yeah, I have to change omega, because the only way to get different speeds is changing actually omega. So if this was omega 1, I can give it a different omega. The whole thing will repeat at a different speed. Okay? Good. Now one thing you have to keep in mind, that the basic equation that I equals V, so I equals V minus, let's see how the best way to present it. Oh, so let's do it a different way. The same equation, that's V into the motor equals IR plus the EMF, the back EMF, Okay, this equation is true for any motor, not just for a DC motor, because in any motor there is an internal resistance, there's a voltage drop IR, and in any motor where you have a magnetic field rotating in a coil, there is an EMF generated. Okay? So we talked a lot about the back EMF in DC motors, but there is also a back EMF in AC motors. In AC motors, it's a bit more complicated because there is also an inductive component. So actually, the R in an AC motor is not only R, but it's actually Z. Because the way they draw the model, in a DC motor, we drew IR, and then we drew, that was the back EMF created by the rotating rotor, and this had to be equal to V. Now in an AC motor, so this was for DC. So in an AC motor it's a little bit more complicated because the input is actually AC. So now you have IR, but you also have some losses because there is some inductance to the coils. Okay? So you actually have also J omega L, J because it's 90, and now you have the back EMF. And the back EMF is also a complex number because it's not exactly at the same phase. So it's a little bit more complicated, but the general idea is the same. And I don't want to get too much into the electrical engineering part because I know most of you don't have the background. So the general idea still looks the same. Okay, so what that means that if you lower the speed of the motor, like you give it instead of omega 1, you give it omega 2, the back EMF will go down proportionally, because say if the armature is a permanent magnet and it rotates in a coil, if the magnetic field rotating vector is slower, the armature goes slower. But if the armature goes slower, it also generates a smaller back EMF, because the back EMF is proportional to delta phi to delta t, and delta phi is simply the omega. Okay? So what it means that I also, when I lower the frequency, I also have to lower the voltage. Okay, so this is actually done. This is omega 1 done at, say, V1, but if I lower it to omega 2, I have to lower also the voltage, but just lowering the voltage will not change the speed. If I keep the frequency constant and I just lower the voltage, all what happens, I'm limiting the torque. Because the I cannot, if this is lower and this is the same, because speed is the same, then IR has to be lower, which means I has to be lower. Okay? Because remember, torque is proportional to I. So if I give it a lower voltage, the same EMF, then I has to go down, torque goes down. But if I intentionally want to change the speed and I lower omega, there will be less back EMF, so for the same torque or the same current rating, I have to lower the voltage. Okay? All these variable frequency drives, like the one I showed you the demo with, when you change the frequencies, they automatically change the voltage. They are programmed for it. Now the reason I have to change the voltage, because the motors are rated by a given current. The motors are made with some copper winding. This copper winding can carry so many amps. So whatever you do, the thing which causes heating in the motor is I squared R. Especially not the voltage which causes the heating, it's the current. So inside that motor there's a heating of I squared R, and the motor is rated for a certain heat dissipation. So if the motor is rated, say, for 10 amps, whatever you play with frequency and voltage, you cannot exceed the 10 amps continuously. Right? Maybe for a second you can, but continuously the motor has a rating. The rating has to do with the cross section of the copper winding. So the motors are rated by current, not by voltage basically. When you look at the nameplate of a motor, it says voltage and current, but the voltage is for 60 Hertz, for standard frequency. But when you start playing with the frequency, you have to change the voltage not to exceed a certain current. Okay? So here it gets a bit more complicated. If you just change the voltage without changing the frequency, you just limit the torque. If you want to change the speed, you have to change the frequency and the voltage. And the reason why you have to change the voltage is if you lower the frequency, you are also lowering the EMF. If it's not fully clear, just rewrite this equation. Rewrite this equation that you say that I, the way we wrote it for the DC motor, I is V minus EMF divided by R or divided by Z. Okay? So if I lower the frequency, the EMF goes down, so this number becomes bigger, so I have to make this number smaller as well to keep I constant. Basically what I want is V minus EMF to be constant, because this divided by R is the current. Okay? So if I lower the speed, this goes down, I have to make this go down to keep I constant. Is that clear to everybody? Good. Okay, so this is a family of curves of a synchronous motor. And now if we make a family of curves for an induction motor, it's a little bit different, because unlike a synchronous motor, which cannot take any bigger load and it collapses, an induction motor, this curve actually exists. Because an induction motor, it doesn't lose all the torque, it just starts slipping more and more. So because of that, it's a bit different and has a more desirable characteristic. Now, I'm reminding everybody, the reason why this is very undesirable is when you start a motor, you always exceed the rated torque. Because when you start a motor, there's inertia. So the very first few milliseconds, the inertia doesn't allow the rotor to move as fast as the rotating field wants. So when you start the motor, the first minute, there is always a high torque. So if this motor collapses at a high torque, it doesn't want to start with any inertial load. And that's, as I mentioned, the only disadvantage of synchronous motors. They have no starting torque. Because to start, the moment you start, an omega ramps up instantly, because when you start the motor from the power line, you apply the full omega instantly. So the moment you apply the full omega instantly, it already wants to turn at full speed. Because of the inertia, it's already at this point and collapses. Good. So now let's talk about induction motor. So this was synchronous motor. Now this is induction motor. So if this is omega and this is torque, we said if this was synchronous speed, omega s, say, this point was omega s, meaning the synchronous speed, the way it will work, it has to have slip to generate an induced current in the armature. So at zero torque, it may have near zero slip, and it has a small slip which I'm drawing exaggerated. So this is as you increase the torque, you need more current to supply the torque. The way you create more current, the armature slips behind the rotating field, so it sees a frequency which is a difference. It's clear to everybody why the frequency the armature sees is a difference between omega s and the real omega? Good. So at some point, which is optimized by the motor design, it reaches some peak torque, like this. Now, if you try to give it more, you can't get more torque than that, but if you stalled the motor, it doesn't collapse, it actually goes like this, okay? It actually has some torque at zero speed. So if you start the motor, it's stalled and you start, it doesn't start from zero torque, it starts from this torque, and as the speed goes up, so this is the starting point, the resting point. As the speed goes up, the torque actually is improving, which is counterintuitive. Because usually you start with the biggest torque, and if the speed goes up, actually you get less torque. Here you get more torque. Now the only reason for that is the motor is optimized for a certain working point. If you just didn't optimize the motor, it will look a bit different, okay? If you didn't optimize the motor, when I don't want to draw it, not to confuse you, I draw it separately. If you didn't optimize the induction motor, it will look like something like this. It will have the biggest torque at zero speed, because at zero speed, the frequency which induces current in the rotor is the largest. Okay, so you get the biggest current in the rotor, you get biggest torque. But you don't like that, because you like the motor to work here, and you're trying to get the highest efficiency here. So you optimize the copper or the aluminum and the steel and the gap, and the whole thing is optimized that it has the biggest torque, which also means the biggest power, because it's running almost at constant frequency at a working point, and you always run the motor at this point. If you load it a bit, it will go to this point. If you unload it a bit, it will go to this point. But basically, it's always working at this point of the rated torque. If you take away the load, it will just run up here to a lower speed. Okay? So this is like a low load, and this is full load, and this is, if you go too high above full load, it's not going to work. Because if you try to get the torque higher than this point, it's not going to work, it's going to stall. But as soon as you remove the load, it'll climb back up. Yes?
What's actually done to the motor to optimize it? What does that mean to optimize?
Okay, what it means to optimize it, you're trying, the induction motor is really a transformer. Okay? So because what happens, as I drew before, you have coils here, and you have a rotor here with the equivalent of a coil which is shorted. Okay? Now, when you have a model of a transformer, did you learn in electrical engineering what a model of a transformer looks like? I can just explain very briefly. Okay, if you model a transformer, because this is like primary, this is secondary. So if you model a transformer, the model looks like this. And I'll explain in a minute. And this is shorted. This is shorted. And you also have this, and I'll explain what it is. Okay, this is the R, which is understood. This is L, which is the inductance of the coils. But and this is an ideal transformer. This part is an ideal transformer which has no losses, no R, no anything. Okay? And again, this is R, this is L. This is L leakage inductance. Okay? So when you look at the model of a transformer, if you increase the frequency, this current not necessarily gets higher. Because you increase the frequency, this becomes a concern, this becomes a concern. Because an ideal transformer has no inductance. And you have to think about this for a moment, because an ideal transformer just reflects this resistance. If this was a one-to-one transformer, an ideal transformer, and you put a resistor here, you just see the same resistance on this side, you don't see inductance. Okay, so the inductance is a parasitic effect in the transformer, which comes from flux which doesn't engage both coils. So if you have physically a transformer and you have two coils, you want all this flux to engage the other coil, but some flux goes without engaging the other coil. So this part of the flux just looks like an inductor. The flux which couples both, it doesn't have inductance. So I know I'm going very fast through it, but so when you take a transformer like this, at zero frequency, there is zero current here, because there is no change of flux. But at a very high frequency, there is also zero current here, because at very high frequency, this inductor, which is will limit the current. Okay? So if you draw I, which is the same as torque in a motor, if you draw I versus frequency, it doesn't look like this, like it would look in an ideal transformer. It actually looks like this or something. So you can optimize this point by playing around with how much copper, how much iron, how much resistance, and so on. Because every transformer, if you look at a wide enough frequency, looks like this. Because at very high frequency, the transformer doesn't work. Okay? So optimize is where to put the maximum point. Okay. Of course, there are other factors like the type of laminations, because again, there's hysteresis losses. There's many other factors. So altogether, it's optimized to work at near omega S, and I gave you an example that it works typically 5% below omega S. So this point is typically 5%. If you want a better number, like the typical motor in your home is 1800, omega S is 1800 RPM. I'm just writing it in RPM, not in radians per second, because that's what the motor nameplate says. And actual omega this motor works is 1725. That's a standard motor in your furnace, in your washing machine, and all the stuff at home, except your table saw. Okay? So what we're talking about is this, the slip frequency. We're talking about 75 out of 1800, okay, which we said it's roughly 5%. Okay? If it was 90 out of 1800, it would have been 5%. Okay? Let's say 4%, let's say. So in round numbers, it's a constant speed motor. It runs at 96% of synchronous speed, which is close enough. Okay, so what happens here if we lower the voltage? Let's say if you take this motor, give it a lower voltage, what will happen to this curve? Okay, will it start from the same point at a lower voltage? Yes, it has to start from here, has to start from synchronous speed. So lower voltage means less current at the end, because it's back to this equation like before, that the current is the difference between the voltage and the EMF divided by the impedance or resistance. If you have less voltage, you have less current, less torque, so it can't reach this torque. It can only reach a lower torque. So it will have to look like this. So this will be V1, this will be V2. Okay? Maybe it will be less optimized, but in general the curves will look like this as you lower the voltage. Very much like those things here, except here the speed is completely constant at a lower voltage. Here the speed is almost constant. I'm reminding everybody again, this is highly exaggerated so you can see it. If you drew it to scale, this is 4%, right? So again, if you drew this graph to scale, it will look like this. It will look, these things to scale will look almost like a flat line, because that drop is only 4%. So I'm drawing it exaggerated just so you can see. Okay. Good. Now, how do I change that speed? If I want to change that speed of the working point, this is the working point. If I want to change the speed, what do I have to do? Frequency. I have no choice here. It's a rotating field motor. The only way to change a set of curves. So if I want a different speed, it's too bad there's no color chalk. But anyway, if I want a different speed, I have to go like this, and with a different omega s. Okay? And I have to adjust the voltage, same as here. If I go to half the omega, I have to roughly half the voltage, because the EMF will also be half. So back to I equals V minus EMF divided by R, or maybe divided by Z in a more complex model. So if I half the speed, the EMF is half, so I also have to lower the voltage to get the same current, because the motor is limited by current. Okay? So here when I go to omega s, I also have to use a different voltage. So this is omega s1. This is at V1, and if I go to omega s2, synchronous speed, I also have to go at V2. So just changing the voltage doesn't change the speed. Just changing the voltage changes the torque, the maximum torque. If I want to lower the speed, I have to change the frequency and the voltage. Same as here. So you see what's more confusing here, because on a DC motor, there was only one parameter in control, voltage. That's it. Because even the torque I can adjust with voltage. If I want at some point more torque, I just can increase the voltage, the motor will give you more torque for that load. So it's really 1 degree of freedom, okay? Now, in this motor, no matter what you want to do, you have to adjust 2 parameters. Okay, so if you want a new operating point, unless the operating point is the same speed, okay, if you want a different operating point, meaning different speed, different torque, you have to always adjust 2 parameters, the frequency and the voltage. Clear? Good. Okay. So, let's talk a little bit about power. Okay, so because in many applications, say if you build an electric car, you're interested in power. You're not so much interested in torque for torque's sake. You're interested in power because the car has, at one point, kinetic energy of 0. A few seconds later, you want it to have a kinetic energy of 1/2 mv squared. So how fast it can get from A to B depends how much power you can generate, okay? So now if you plot power, so now I'm plotting a different set of curves, power versus omega, okay? So if you look at a PMDC motor, which is almost constant omega, where torque goes up, so if the motor is limited, say, to a given torque by the wiring, it can only take 10 amps, so it gives you a certain torque, and you give it more and more voltage, you will give more and more power. So I'm drawing here it's a limit. If the motor is limited to a certain current, and if I increase the omega by increasing the voltage, so a PMDC will look like this. More speed, more power. Good. A series wound motor, as we discussed before, because of its nice 1/x behavior, will look like this. Power is constant. Because a series wound motor, torque times omega is constant, and torque times omega is power. Okay, so power will be constant. Okay. Now, how will a synchronous motor like this look on this curve? So this is the series motor. Okay, now how will a synchronous motor look if I adjust omega and V to maintain the current always at maximum? Because remember, to do a fair comparison, I have to run all the motors at rated current. So now I take a synchronous motor, adjust the voltage for each omega, and it's running always at constant current. What will the graph look like? Pardon? Linear, very good. Look exactly like PMDC, because the torque will be constant. If I play around to get constant current, I'll get constant torque. And now if I get constant torque and I change omega, power is torque times omega. So if I play around to keep the current constant, it means I'm playing around to keep the torque constant. If torque is constant, it will be the same, exactly like PMDC. So this is PMDC and synchronous motor. Okay? Now, what will this look like if I play around to keep the current constant? So I change omegas, but I always adjust the current, so this point is the same. The torque is the same, because I'm playing with the current always at full current. Okay?
Close to linear?
Pardon?
Close to linear?
Oh yeah, pretty well the same. Basically, hysteresis, induction, and PMDC. So all of these look the same if you draw power versus omega, except a series motor which is constant power, which is very desirable. Because remember, constant power means a huge starting torque. Because constant power at 0 frequency means infinite torque. So that's why this PMDC is such a nice motor. It's as I mentioned, I gave you the analogy that not PMDC, sorry, a series motor which gives constant power, that is equivalent to a motor which has the ideal automatic transmission. Because the purpose of an automatic transmission is always to match the power of the motor to the load. So if you have a regular car, when it starts, you go to a low gear, because when it starts, you need a lot of torque at low speed, so you have to gear down a lot, so you can use all the power of the engine. And as you speed up, you gear it down less and less, but you're trying to always get the maximum power. A series wound DC doesn't need that. Series wound DC always gives you constant power, so So if you saw from that graph, the torque will go to infinity at 0 speed. Okay? So that's why this is a motor which has the best acceleration. So if it's a motor which has the best acceleration, because it's always full power, why don't they use it in electric cars? So we talked about it before. We said the series wound DC motor has some marvelous characteristics. It's used in all power tools because of these characteristics. But why isn't it used in electric cars? What's the big problem with the DC motors? Say it loud. Somebody said it here. Sparking, yeah. So, the reason you don't like in electric cars, it has a commutator which sparks and wears out. The sparking, to remind you, have two bad effects. RFI, right, it sends a lot of electrical interference, and it wears out, mechanically and from erosion. Mechanically it wears out just from wear on the brushes, but also it erodes, because each time you have a spark, it actually vaporizes sub-micron amount of copper and graphite. So eventually the combination of the mechanical wear and the sparking will erode and needs maintenance. That is exactly the reason why cars used to have a dynamo with brushes and got replaced by an alternator, which has slip rings but no sparking. Because the slip rings are continuous, they don't interrupt the current, there is no sparking. That was a huge improvement to put alternators instead of dynamos in cars, because there's nothing to wear. Okay? So in spite of this wonderful characteristic of PMD, of series wound, all electric cars, except the very old ones, use an induction motor. Now the reason they have to use an induction motor and not a synchronous motor is just a synchronous motor would not start. You have to start very slow to keep it in lock. And an induction motor will start from 0 speed and ramp up to the right speed. Okay? Now, because of the need to change the voltage when you change the frequency, you cannot keep this graph on forever, because this graph implies you could go on forever, because this graph is still under constant current. So when you run the motor here, it doesn't get any more hot than here. Because what heats up the motor is I squared R, plus a bit of air friction, plus a bit of hysteresis, but the main reason the motor heats up is I squared R, but we are keeping I constant. All these graphs are under the assumption that I is constant. So that means that the motor running here, or the motor running here, has the same heat. So why not run the motor here and get even more power out of it? So can somebody think what actually limits this graph? Why can't you run the motor faster and faster and get more and more power out of it if the heat doesn't change? Yes?
Analytic saturation of iron ore.
Actually not. It's a good guess, but actually not, because if I is constant, B is constant. Because what creates a magnetic field in a motor is I. So if I keep I constant in this graph, in order to keep I squared R constant. So if I keep I constant, I also keep B constant. So here or here, there's no difference in B. Yes?
Mechanical limitations of bearings and such?
Mechanical, but you can run a motor pretty fast. The bearings, you know, if you look at a router at home, it runs at 20,000 30,000 RPM. Like in a Tesla, the sports version ran up to 18,000 RPM. The passenger version, Tesla S, runs at 8,000 RPM. Okay? So let's ask a different question. Why don't they run the Tesla S at the same motor speed as a sports car? So basically, there must be another limitation.
Batteries?
Pardon?
Batteries?
And what about the batteries?
Well, you're going to run out.
Ah, okay, yes, but still you want a lot of power. It doesn't waste the batteries because you don't have to use the power. That power is only used when you need it. When the car doesn't take so much power, you can run it at a different point. It's not less efficient. So in terms of batteries, it doesn't matter. But something else must be the limit. Yes?
Inductance goes up with frequency?
Ah, so there is two limits. One limit is we drew in this model. We said there is also an inductance, And as you climb up here, it also means you increase the frequency. And as you increase the frequency, this gives more and more trouble. So that is one reason, and there's a second reason. Yes?
Need to increase the voltages?
And that is a real reason. Because as you increase the speed, the back EMF increases. So you have to keep increasing the battery voltage to keep I constant. Because always go back to this equation. I is V minus EMF. But now I'm increasing the EMF by increasing the speed. I have to increase V. So eventually the batteries run out of voltage. So for example, in a Tesla, the batteries are about 300 volts, something in that order. But if you really wanted to run it faster, it just wouldn't be enough voltage. So in practice, what happens? The graphs look like this. This is P, this is omega. It runs like this, which is constant P, and then flattens out. This is constant V. Here, constant V, because you reach the full battery voltage, that's it. Okay, so what happens here, when the power reaches saturation, because as you increase omega, the torque falls down. See, when you increase the battery voltage and the RPM goes up, the torque has to fall, because torque is proportional to I. So if this is fixed and the EMF goes up and up and up, I starts falling, because V minus a ever increasing value divided by R. Okay? So let me just draw under this a torque. This was power. What I drew here is power. Let's just draw torque versus omega. So up to a certain omega, torque is constant because I is always running at the maximum. But at some point I can't increase the voltage anymore, and then I get I dropping and I get this. And so this curve is no longer constant I. This curve is actually constant V. Okay? So because of it is constant power. So the power looks like this. Is that clear to everybody? Okay. Anyway, to make it more clear, I'll pass around the actual graphs from a Tesla, so you can look at them and think about it. Okay, and then we'll put it in the video too, so just have a look and pass it around. Yes?
So is the voltage in the roadster that they have much higher than
No, the motor is different, because you can design the motor by number of turns to reach a certain EMF. So if you lower the number of turns, it will need more RPM for the same EMF. So the way you design the motor for a given voltage is by the EMF, by choosing number of turns. Now if you have less turns, you can use a thicker wire. If you use a thicker wire, it has more torque. So the power of the motor doesn't change. If you make a motor with less turns, heavier wire, it has less voltage, okay, but more torque. So the torque times the RPM is constant. So the power, you can gain some power by running the motor faster in a smaller package, but in general, very crudely speaking, the power doesn't change very much. You can you play around with the current and the voltage on the coils. So you do gain power, because typically if you really want to make a motor to run at a low voltage and efficiently, you have to make it with many poles, because otherwise you end up with a very low frequency. Okay, so if you make it with many poles, it has many windings, it becomes bulkier. So if you really want a very high performance motor in terms of horsepower, you are better off making it small and very high RPM. The only side effect is noise. The bearings are not a big issue. You can use ceramic bearings, which Tesla uses, and you basically get infinite life. So the real issue becomes noise. It makes a whine. Like 60 Hertz is very low, not an annoying noise. But if you run a motor at 60,000 RPM, which means 1,000 Hertz, you'll get a very annoying whine. Like if you go to a dentist, the dentist drill is 200,000 RPM. And nobody seems to like that noise. So somehow there is a shrill noise from high-speed motors, and in a passenger car, people don't like it. So I believe that's the main reason why they cut the motor speed. Because in terms of horsepower, you could have gotten the same thing from a slightly smaller motor if you ran it faster. The noise is also from the gearing. Remember that if you have an electric car, the motor is running at 10,000 RPM, you have to gear it down to the wheels, right? But the gearing also makes noise, because if the teeth have to engage at a much higher speed, the gear is much noisier. Okay, so any questions about this performance curves of the different motors? Okay. Here is an interesting question. How do you actually measure this? What is the most elegant way to derive these curves? So somebody gives you a motor and says, plot these curves. What do you physically do to derive these curves? Does somebody know? So I'll let you think a minute about it and see who can come up with the most elegant way. Okay, so did somebody figure out how to derive these curves? So let's start with a historic way. Like even at James Watt's time, they already had curves for engines. Actually, James Watt was the first person who applied scientific methods to optimize engines. He invented what's called the steam engine indicator, which is a device which plots the PV diagram in steam engines and car engines. V here is volume, not voltage. You saw these diagrams in mechanical engineering courses. James Watt was the one who came up with a unit which plots this, the indicator diagram. Okay, so they had not just PV plots, but torque versus speed plots already in James Watt's time. So how did they do it at the old days? So in the old days, the typical thing was there was a motor. The motor was actually a steam engine, but it doesn't matter. There was a shaft. You put a pulley on it, okay, and you put a brake. I draw it from here. This is a pulley, and you put an actual wooden brake on the pulley, and let's say the motor was turning this way, and you put a weight. You put a weight here, and this slipped. You tightened the brake, and you let the motor slip until it balanced. So when it balanced, this was M, this was L. So you knew the torque was M, in this case mgl. So you knew the torque and you knew the speed. The speed you can just count 1, 2, because this motor is very slow. The old engines were slow enough. You can just count by eye how many rotations per minute they did. Okay. So basically, you wanted a different point, you clamped down the brake more, increased the weight more, until it slipped again. So this didn't move. You had a stop here and a stop here. So this arm had to stay between the stops. It didn't swing around. But you played around for a given friction. You played around with the weight until the arm stayed floating, and then you knew that that friction torque is mgl. Okay? And then you did it for different speeds, and you had a set of points. Okay, so if this was torque, this is omega. You had, say, 3 torques based on 3 adjustments and 3 omegas. Okay, but that's quite tedious, because for each point you have to adjust the friction. Okay, so that's a classic way. It's called a pony brake. That basically has been used for 200 years. But today, with all electronics and tricks, there must be some more elegant way. So, any ideas?
Dynamometer?
Pardon?
Dynamometer?
Okay, so what is a dynamometer?
Uses water to increase the torque on the...
Okay, correct. Okay, so one way to do is you put a load which is variable. It doesn't have to be water. The load can be a generator. So you can take the motor. You can take the motor and connect it with a coupling to a calibrated generator. And the generator, you can change the torque by the load resistor. So this is a generator and this is a motor. And this whole setup is called the dynamometer. And when you go and get your car tested for emission, once in a few years you have to take your car to the testing station, and they put the car on rollers and run at different speeds. That's what they do. This is your car, it's driving a generator or they change the load. And here you can measure the speed of the generator by the voltage or by the RPM. Let's say it has an encoder. It's very easy to measure the speed, it's easy to measure the torque, okay? And that's called a dynamometer. It also can be done with water, with friction. The best way to do it is just a generator. But surprisingly, this is a dumb way of doing it, okay? I mean, that's kind of the most obvious way, but not the most elegant way. So there is a much smarter way of doing it, which doesn't require that. Okay, so I'll show you how it's done. All what you have to do is you take the motor and you put a very big flywheel on the shaft. Okay, so this is a flywheel. Okay, and all what you do is you take a shaft encoder okay, or if you don't have an encoder, just even an optical switch which gives you 1 pulse per revolution. Okay, so if you look, you want to plot omega versus torque. Okay, so if you look at the encoder output, or this could be even a small generator, DC generator, anything which picks up the speed. Today the simplest is just a cheap optical encoder, maybe with just 100 pulses. So this gives you omega. Okay, so you can connect this, say, to the computer, to the y-axis, or to a scope, to the y-axis. Now, how do you get torque? How do you get the torque from this setup? Pardon?
Torque equals the moment of inertia times that.
Torque equals what?
Times the, oh, you change the omega, so the torque equals J alpha.
Yeah, but how do I measure the torque?
You have to know the moment of inertia of the...
And how, okay, so let's say you know the moment of inertia I, okay, that's the moment, or J. I know the moment of inertia, okay, let's call it big J, not to confuse it with current. So I know the rotational moment of inertia, and then what do I do? But I want to plot it. I want to have a whole bunch of points. If I stop it, I only get it at omega 0. But I want to have a whole bunch of points at any omega. I want to know the torque at any omega. No, it turns out a much smarter trick, because if you look at it, the acceleration, the rotational acceleration, okay, let's call it omega dot. Are you familiar with the dot and double dot? Okay, so omega dot is simply the torque divided by J, okay? So if I can take, so basically the torque is simply J times omega dot, okay? So all that I have to do is I have to take the derivative of this. And that's very easy to take the derivative. I can do it if it was a DC voltage from a generator, I could just put a capacitor and a small resistor, and this will give me the derivative. With a computer, I can do it numerically. If I take this is a voltage. Let's say you convert this to a voltage. To make it simple, I feed it to a computer and I take the derivative, and then I connect the derivative, omega dot, or d omega to dt. Okay? So basically it's J d omega to dt. I connect this to the x-axis, I connect omega to the y-axis, and I turn on the motor. The moment I turn on the motor, it goes through all values from omega 0 to the maximum omega, and the moment I turn it on, it plots this graph. Okay? Is that clear to everybody? So all what you have to do is you have to know J. Now some people say, just a minute, you don't know J because the motor has some internal inertia that you don't know. Okay? Which is true. You just know the weight that you added, but you don't know the internal inertia. So how do you get around that without complex measurements? Yeah, exactly. All what you do is you either add another J or do it without the J. You do two plots, one plot without the ring and one plot with the ring, because now you have two. If you have one more unknown and one more equation, right? So it's the same as adding another one. Okay. So you say this is J1, you add J2, and J2 could be the motor inertia. Okay. Now, but in this case J2 is not known. However, if you do that, you'll get another plot, and between the two plots you can calculate what the internal J is. Okay? So basically the most elegant way to plot torque versus omega is just let the motor start and just monitor the speed. Okay? Good. Okay. Now remember, this of course doesn't work for motors like a synchronous motor which cannot start when you put it a big load. Because the synchronous motor is more complicated. You have to run it at a given speed and then you have to apply the torque. But for all other motors this works. Okay. So now so I think this more or less covers the motors. Good. Let's see. I just had a checklist here to see if I covered all the motors. Okay. Yeah, there's a couple of other small items. One small item is when you use these motors in servo systems, there is another parameter which is usually never mentioned, but it's critical. And that parameter is called cogging. Or it's also sometimes called detent or detent torque. Now what this means that a motor has a natural structure inside. When we talked about a stepper motor, we said a stepper motor inside has 50 poles and they can be smooth or salient. Salient means sticking out. And then it has a stator which has slots with winding. And I mentioned there is some natural detent position where the magnets like to line up with these salient poles. Okay? Now, when you drive it with a rotating vector, if the flux distribution is perfect and the coil arrangement is perfect, it will just rotate smoothly with a vector. But you still can see the signature. Of the detent, of the positions it likes to snap into. Okay? So what it really means that if you look, if you draw, say, this is pulse number, this is number of pulses, and this is position. A stepper motor will not be exactly a straight line. It will actually have a tendency to do this because it will pull itself into its natural positions. Okay? The same thing you feel when you take a stepper motor and you turn it without power. You feel it does tick, 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 tick. It doesn't go smoothly because you feel those natural positions. Okay? So again, if it was perfectly laid out inside, the flux was perfectly distributed, under power it wouldn't have that. But there's always a signature. Now in other motors it's the same, and I mentioned the typical solution in motors is in the armature to slant a bit the slots to slant them a little bit to get a smooth transition. Okay? In a stepper motor you can't do that because this is only 1.8 degrees. There's not much room to slant. But in bigger motors it's slanted. But in spite of this, there is always some kind of lack of smoothness, which is if you draw it, say if you draw torque versus angle of rotor, say from 0 to 360 degrees. Because you imagine after one rotation it will repeat itself. So an ideal motor looks like this. The torque is constant no matter where you are. But most motors, the torque changes because at some positions the air gap is less, because you can imagine when these magnets align with the slots, there is more air gaps than the magnets align with the laminations. So in most motors, around 360 degrees, there is some kind of a thing like this. It has to come back to here, which usually this is a number of poles inside. You can sense the number of poles. And this is called cogging. Now, the two terms are not exactly the same. Usually, cogging refers to this torque variation under power, and detent torque usually refers to the natural detent action, even if there's no power. But to make things simply, we'll use them interchangeably. Now, why is that bad? Why do we care, actually? This appears in all motors, by the way. In DC motors, if you have a DC motor, it's the same, because the air gap changes. Right? If you have a PMDC NS, and you have an armature like this, with 3, and these are the poles, you also have variations in the flux, because this way the flux is a bit different than the armature is rotated a bit, okay? So there is also flux changes, so this problem appears in all motors. So why do we care, actually? Because the servo system is going to position it. If the motor has an encoder, the servo will position it correctly, so why do we care?
Non-linearity in the control?
Correct. What it is, it's actually not even non-linearity, it's fluctuating gain. Because we give it a current, we want to have a torque. So if we look at the block diagram of the whole servo, so there is a block there, which is the actuator. Input is current, output is torque. But if the output depends on the position, okay, it behaves as a nonlinearity, although it's still a linear system, but it's position dependent. So what we have an amplifier. If we draw the servo, and this was a block, the block called plant, or the block called actuator, it doesn't have a constant conversion, so many torque per amp. The conversion depends on position. So if this varies 10%, and that's typically what it is in a regular motor, it is the same as the gain fluctuates 10%, and that's not so good, because in some servos we like to make a perfect model and we need to know the exact gain. Okay? So because of that, the motors which are designed for servo systems, they try to minimize this. And somewhere at the bottom of the spec sheet it says cogging torque 1% or 2% or 3%. In an industrial motor it's never specified because nobody cares. There is a few other things in the spec of a servo motor which don't show up in the spec of a regular motor. And for example, in the spec of a servo motor, the most important thing is the ratio of torque to inertia. Because ratio of torque to inertia is how fast it can speed up, right? Because we said that's the acceleration. Angular acceleration is torque to inertia. So in a motor which has to drive a washing machine, it doesn't matter if it speeds up in a second or a millisecond. But in a servo motor, that's the key thing. That determines the bandwidth of the servo. So in a spec of a servo motor, there is a torque to inertia ratio. Sometimes it's given as a time constant. Sometimes it's not given as this, but it says electrical time constant, and it says mechanical time constant. Okay? So electrical time constant just means the R over L, how fast the current can rise, limited by the inductance. And mechanical time constant is basically dependent on torque to inertia. Okay? Mechanical time constant means in how many milliseconds it will reach 1 minus 1 over e, like 67% of speed. Just like time constant is defined in a capacitor, right? So this is that's how fast it can accelerate, and this is how fast the current can go up, because the motor still has parasitic inductance, and this is the EMF. The parasitic inductance has a time constant, which is L over R, and that time constant, so it's L over R, not L over R, not R over L. So this L over R, which is the time constant of an inductor, this is R, this is L, this determines how fast the current can come up, because the torque cannot develop until the current came up. Is that clear to everybody? Now that's especially typical in stepper motors, because stepper motor has a lot of windings, okay? And because you want to generate, has a lot of coils, a lot of slots, so has a lot of poles, so it has a lot of windings. So in a stepper motor, actually, this is a big factor. The electrical time constant, how fast the current can come up, that is a limiting factor actually in a stepper motor, because it has, relatively speaking, a lot of inductance for its size. And how do you solve that in a stepper motor? So if I connect a stepper motor and I look at I, and this is T, the I cannot come up immediately. It typically takes a few milliseconds, because the I can only go up as E to minus T over L over R, so TR over L, yeah. So what do I do in stepper motors to mitigate that? So if I want to drive a stepper motor fast, and I know the current cannot go up right away because of the time constant, what do I do? Well, you know from experience, what did you do when you built stuff with stepper motors and you wanted them to go fast? You drive it with a constant current drive, not with a constant voltage. Because if you have a high enough voltage available, and the stepper can take a certain current, like 1 amp, you can force that 1 amp current with a constant current drive. So in a normal stepper drive, if this is T, and this is I and V, so V looks like this is V, you step up the voltage, and I looks like this is I. Okay, I climbs slowly because of the inductance, but you can do something else. You can take and force a constant current. So you can do this is I, force I to jump up right away, and then what will V look like? Theoretically, it will have to go to infinity and come down. Because theoretically, if you want to change the current from 0 to I, the voltage you need is L di to dt. And if you want to change di to dt instantly, you need an infinite voltage. So what you do, you do a compromise. You make the I with a certain slope, pretty fast slope, so the V doesn't have to start from infinity, but starts from very high voltage. So typical drive of a stepper motor, if the working voltage is, let's say, 5 volt, so typical for a stepper motor, you actually start with 50 volt. So say this will be 5 volt, and this will be say 1 amp. You'll start with 50 volt drive, so it will be almost like constant current. Okay, so this will give you a much faster rise time. Is that clear to everybody? So in all your labs, when you have stepper motors and you have a box called micro stepper driver or stepper driver, that's what these boxes do. They try to drive at constant current to overcome the inductance. So to summarize, when you look at a servo motor spec, you look at all the normal specs. You look at torque, at current, at size. You look at all the specs you look for any motor, but you have to look at 3 other specs. One is the electrical time constant, one is the mechanical time constant, which is basically, or the inertia. But what you really care is inertia and torque to inertia. And the third thing, which nobody looks at, but you should for critical servos, is cogging. That's usually at the bottom in very small print and sometimes doesn't exist and you have to phone and ask. But for a critical servo it's important. Because say if you run a motor at a constant speed against a constant torque, because of the cogging there will be minute speed fluctuations. Because let's say you're holding the motor back at a constant torque, but if there is cogging and the torque, you're trying to hold it against a constant torque, what will happen, the speed will fluctuate. Because at some point it has a bit more torque, so at some point it has a bit less torque. Okay? So when you say you have a rubber band attached to the motor is trying to wind it up, it actually, the speed will fluctuate a bit like this graph. And this happens at a high rate. It's sometimes difficult for the servo to remove that. Say if a motor has many poles, and this is quite a high frequency disturbance. Okay, now if motors are designed for very high performance servos, they also have a different construction, because if you look at the PMDC motor, typical PMDC motor, you want to minimize the torque to inertia ratio or maximize torque to inertia, so you're trying to minimize inertia. So if you look at the armature of the motors I showed you, they had a piece of steel. The armatures had a piece of steel and then they had coils on it. So they had a lot of inertia because you have to rotate the piece of steel. Okay? So if you take apart very high performance PMDC servo motors, they don't have steel. They only have coils. But if you don't have steel, you can have a big flux because the steel is what helps the flux. So the way they work, you have a magnet in cross section. You have a magnet, NS. Now you have a coil which looks like a cup. You have a coil which looks like a cup connected to a shaft. So this thing is a winding, and then you have a piece of steel inside. So what happens, the flux still has a small air gap, but the piece of steel doesn't rotate, only the cup rotates. So I'll draw it in 3D. The rotor looks exactly like a cup, open from this side and has a shaft. And it's wound with wire and epoxy to be self-supporting. Okay, now inside here you either put a piece of steel or a magnet, and outside you put a magnet. Most of these motors are reversed, the magnet is inside just to minimize size. Okay, so if I look at this motor from this side, what I see is I'll draw it here. I see a steel ring which is just to close the magnetic flux. Now I see a permanent magnet which is sitting inside and closes the flux to the steel, but this magnet doesn't rotate. And then I have a cup which goes in here. So this is a cup, okay, and this cup has a winding on it and has a shaft from one side, and it rotates in the air gap. Okay, is that clear? So is the geometry clear? Imagine a teacup that has a magnet on the inside, a ring of steel on the outside, and the teacup can rotate in between, but the teacup is made of winding. So this is the most popular construction for a high-performance DC servo motor. For example, the motors made by Portescap, or all the standard names of when you buy a high-performance DC servo motors are all a bit like this. Okay? It has some limitations, of course. It's weaker. The armature is weaker. Okay? There is actually a better way to build a DC servo motor, and to my surprise nobody does it. I mentioned in many other areas there is some obvious better solution which nobody does, like with the encoders. There is an obviously better solution to build a DC servo, but nobody does it, and I can't understand why. And this is to have a shaft, to have the magnet inside the shaft on bearings. So the magnet is sitting on ball bearings, either the magnet or a piece of steel, it doesn't matter. So the magnet can freely rotate on the shaft. Okay? And now to have the winding around it as a shell connected to the shaft. So this is a commutator and this is a winding, and the winding is a shell, and then to have the ring of steel which closes the magnetic path. So this is just a ring of steel to close the magnetic flux. So what happens when this motor accelerates, the magnet is free spinning on the shaft. It doesn't have to accelerate. So looking at this motor from the cross-section, looking at the same motor cross-section, you have a shaft, you have a magnet which is sitting on the shaft on a ball bearing, and then you have a ring of steel. Okay, the flux goes like this. The coil is sitting in between, but the coil can be supported in both ends now. So it can be much more rigid, and when you and this can have salient poles. So basically this ring of steel can have salient poles to encourage the magnet to stay in one place. Now when you accelerate it, this hollow winding accelerates, but the magnet, the shaft rotates, but the magnet stays in place. So you don't have to accelerate the mass of the magnet. Is that clear? Okay? Because in the normal motor today, it's the same as this, but it's cut off here. So the winding is only connected to one end. But you can only build it in small motors. But you can connect the winding in both ends and have a free-floating magnet inside, or a free-floating iron core. And the magnet can be outside. Okay? So the only inertia you have is the inertia of the winding. You don't have to have the inertia of the magnet. Anyway, it's not important. Side note. Okay, so I think this wraps up almost all the motor stuff, and we'll continue Thursday.